Various schemes have been used or proposed for timekeeping on the planet Mars independently of Earth time and calendars. Mars has an axial tilt and a rotation period similar to those of Earth. Thus it experiences seasons of spring, summer, autumn and winter much like Earth, and its day is about the same length. Its year is almost twice as long as Earth's, and its orbital eccentricity is considerably larger, which means, among other things, that the lengths of various Martian seasons differ considerably, and sundial time can diverge from clock time much more than on Earth. Time of day. The average length of a Martian sidereal day is 24 hours 37 minutes 22.663 seconds, and the length of its solar day is 88,775.24409 seconds, or 24 hours 39 minutes 35.24409 seconds. The corresponding values for Earth are 23 hours 56 minutes 4.0916 seconds and 24 hours 000002s, respectively. This yields a conversion factor of 1.027491251 days, sol. Thus Mars' solar day is only about 2.7% longer than Earth's. A convention used by spacecraft lander projects to date has been to keep track of local solar time using a 24-hour Mars clock, on which the hours, minutes and seconds are 2.7% longer than their standard durations. For the Mars Pathfinder, Mars Exploration Rover Phoenix, and Mars Science Laboratory missions, the operations team has worked on Mars time, with a work schedule synchronized to the local time at the landing site on Mars, rather than the Earth day. This results in the cruise schedule sliding approximately 40 minutes later in Earth time each day. Wristwatches calibrated in Martian time, rather than Earth time, were used by many of the MER team members. Local solar time has a significant impact on planning the daily activities of Mars landers. Daylight is needed for the solar panels of landed spacecraft. Its temperature rises and falls rapidly at sunrise and sunset because Mars does not have the Earth's thick atmosphere and oceans that buffer such fluctuations. Alternative clocks for Mars have been proposed, but no mission has chosen to use such. These include a metric time schema, with millidays and centidays, and an extended day which uses standard units but which counts to 24 hours 39 meters 35s before ticking over to the next day. As on Earth, on Mars there is also an equation of time that represents the difference between sundial time and uniform time. The equation of time is illustrated by an analemma. Because of orbital eccentricity, the length of the solar day is not quite constant. Because its orbital eccentricity is greater than that of Earth, the length of day varies from the average by a greater amount than that of Earth, and hence its equation of time shows greater variation than that of Earth. On Mars, the Sun can run 50 minutes slower or 40 minutes faster than a Martian clock. Mars has a prime meridian, defined as passing through the small crater Ares 0. However, Mars does not have time zones defined at regular intervals from the prime meridian, as on Earth. Each lander so far has used an approximation of local solar time as its frame of reference, as cities did on Earth before the introduction of standard time in the 19th century. Note that the modern standard for measuring longitude on Mars is planetocentric longitude, which is measured from 0 degrees to 360 degrees east and measures angles from the center of Mars. The older, planetographic longitude, was measured from 0 degrees to 360 degrees west and used coordinates mapped onto the surface. Coordinated Mars Time (MTC) is a proposed Mars analog to universal time on Earth. It is defined as the mean solar time at Mars's prime meridian. The prime meridian was first proposed by German astronomers Wilhelm Beer and Johann Heinrich Mädler in 1830 as marked by the fork in the albedo feature, later named Sinus Meridiani by Italian astronomer Giovanni Schiaparelli. This convention was readily adopted by the astronomical community. the result being that Mars had a universally accepted prime meridian half a century before the International Meridian Conference of 1880 established one for Earth. The definition of the Martian prime meridian has since been refined on the basis of spacecraft imagery as the center of the crater Ares in Terra Meridiani. The name MTC is intended to parallel the Terran-coordinated universal time, but this is somewhat misleading. What distinguishes UTC from other forms of UT is its leap seconds, but MTC does not use any such scheme. MTC is more closely analogous to UT1. Use of the term MTC as the name of a planetary standard time for Mars first appeared in the Mars 24 sun clock coded by the NASA Goddard Institute for Space Studies. It replaced Mars 24's previous use of the term Areong Mean Time, which was a direct parallel of Greenwich Mean Time. In an astronomical context, GMT is a deprecated name for Universal Time, or sometimes more specifically for UT1. AMT has not yet been employed in official mission timekeeping. This is partially attributable to uncertainty regarding the position of Ares, which meant that AMT couldn't be realized as accurately as local time at points being studied. At the start of the Mars exploration rover missions, the positional uncertainty of Ares corresponded to roughly a 20-second uncertainty in realizing AMT time zones. Each lander mission so far has used its own time zone, corresponding to average local solar time at the landing location. Of the 6 successful Mars landers to date, 5 employed offsets from local mean solar time for the lander site, while the 6th used local true solar time. Mars Pathfinder used the local apparent solar time at its location of landing. Its time zone was AAT02-1301, where AAT is Ares apparent time, meaning apparent solar time at Ares 0. The 2 Mars exploration rovers don't use precisely the LMST of the landing points. For mission operations purposes, they defined a time scale that would match the clock used for the mission to the apparent solar time about halfway through the nominal 90 Sol prime mission. This is referred to in mission planning as hybrid local solar time. The time scales are uniform in the sense of mean solar time, and are not adjusted as the rovers travel. Spirit used AMT plus 110004. Mean solar time at its landing site is AMT plus 114155. Opportunity uses AMT 010106. Mean solar time at its landing site is AMT 002206. Neither rover is likely to ever reach the longitude at which its mission time scale matches local mean time. For science purposes, local true solar time is used. The Curiosity rover local time is AMT plus 090946. With the location of Ares 0 now known much more precisely than when these missions landed, it is technically feasible for future missions to use a convenient offset from Areong mean time, rather than completely non-standard time zones. Sols. The term Sol is used by planetary astronomers to refer to the duration of a solar day on Mars. A mean Martian solar day, or Sol, is 24 hours, 39 minutes, and 35.244 seconds. When a spacecraft lander begins operations on Mars, the passing Martian days are tracked using a simple numerical count. The 2 Viking missions, Mars Phoenix and the Mars Science Laboratory rover Curiosity, count the Sol on which each lander touchdown is Sol 0. Mars Pathfinder and the 2 Mars exploration rovers instead define touchdown as Sol 1. Although lander missions have twice occurred in pairs, no effort was made to synchronize the Sol counts of the 2 landers within each pair. Thus, for example, although Spirit and Opportunity were sent to operate simultaneously on Mars, each counted its landing date as Sol 1, putting their calendars approximately 21 sols out of sync. Spirit and Opportunity differ in longitude by 179 degrees, so when it is daylight for one it is night for the other, and they carried out activities independently while both were operational. On Earth, astronomers often use Julian dates, a simple sequential count of days, for timekeeping purposes. A proposed counterpart on Mars is the Mars Sol date, which is a running count of sols since December 29, 1873. Another proposal suggests a start date in the year 1608. Either choice is intended to ensure that all historically recorded events related to Mars occur after it. The Mars Sol date is defined mathematically as MSD equals 1.02749125 plus 44,796.0, where K is a small correction of approximately 0.00014 due to uncertainty in the exact geographical position of the prime meridian at Areong 0 crater. The word "Yestersol" was coined by the NASA Mars operations team early during the MER mission to refer to the previous Sol, and came into fairly wide use within that organization during the Mars Exploration Rover mission of 2003. It was even picked up and used by the press. Other neologisms include to-sol, as well as one of 3 Mars versions of tomorrow, next-to-sol, morrow-sol, or sol-morrow. NASA planners coined the term soliday at least as far back as 2012 to refer to days off due to time phasing or the syncing of planetary schedules. Martian Year. The length of time for Mars to complete one orbit around the Sun is its sidereal year, and is about 686.98 Earth solar days, or 668.5991 sols. Because of the eccentricity of Mars' orbit, the seasons are not of equal length. Assuming that seasons run from equinox to solstice or vice versa, the season L0 to L90 is the longest season, lasting 194 Martian sols, and Ls 180 to Ls 270 is the shortest season, lasting only 142 Martian sols. One commonly used system in the scientific literature denotes year number relative to Mars year 1, beginning with the northern spring equinox of April 11, 1955. As on Earth, the sidereal year is not the quantity that is needed for calendar purposes. Rather, the tropical year would be likely to be used because it gives the best match to the progression of the seasons. It is slightly shorter than the sidereal year due to the precession of Mars' rotational axis. The precession cycle is 93,000 Martian years, much longer than on Earth. Its length in tropical years can be computed by dividing the difference between the sidereal year and tropical year by the length of the tropical year. Tropical year length depends on the starting point of measurement, due to the effects of Kepler's second law of planetary motion. It can be measured in relation to an equinox or solstice, or can be the mean of various possible years including the March equinox year, June solstice year, the September equinox year, the December solstice year, and other such years. The Gregorian calendar uses the March equinox year. On Earth, the variation in the lengths of the tropical years is small, but on Mars it is much larger. The northward equinox year is 668.5907 sols, the northern solstice year is 668.5880 sols, the southward equinox year is 668.5940 sols, and the southern solstice year is 668.5958 sols. Averaging over an entire orbital period gives a tropical year of 668.5921 sols. Martian calendars in science. Long before mission control teams on Earth began scheduling work shifts according to the Martian Sol while operating spacecraft on the surface of Mars, it was recognized that humans probably could adapt to this slightly longer diurnal period. This suggested that a calendar based on the Sol and the Martian year might be a useful timekeeping system for astronomers in the short term and for explorers in the future. For most day-to-day activities on Earth, people do not use Julian days, as astronomers do, but the Gregorian calendar, which, despite its various complications, is quite useful. It allows for easy determination of whether one date is an anniversary of another, whether a date is in winter or spring, and what is the number of years between two dates. This is much less practical with Julian days count, for similar reasons. If it is ever necessary to schedule and coordinate activities on a large scale across the surface of Mars, it would be necessary to agree on a calendar. American astronomer Percival Lowell expressed the time of year on Mars in terms of Mars dates that were analogous to Gregorian dates, with the 20th of March, the 21st of June, the 22nd of September, and the 21st of December marking the southward equinox, southern solstice, northward equinox, and northern solstice, respectively. Lowell's focus was on the southern hemisphere of Mars because it is the hemisphere that is more easily observed from Earth during favorable oppositions. Lowell's system was not a true calendar, since a Mars date could span nearly 2 entire sols, rather it was a convenient device for expressing the time of year in the southern hemisphere in lieu of heliocentric longitude, which would have been less comprehensible to a general readership. Italian astronomer Mentor Maggini's 1939 book describes a calendar developed years earlier by American astronomers Andrew Ellicott Douglas and William H. Pickering, in which the first 9 months contain 56 sols and the last 3 months contain 55 sols. Their calendar year begins with the northward equinox on the 1st of March, thus imitating the original Roman calendar. Other dates of astronomical significance are northern solstice, the 27th of June, southward equinox, 36th September, southern solstice, the 12th of December, perihelion, the 31st of November, and aphelion, the 31st of May. Pickering's inclusion of Mars dates in a 1916 report of his observations may have been the first use of a Martian calendar in an astronomical publication. Maggini states, "These dates of the Martian calendar are frequently used by observatories." Despite his claim, this system eventually fell into disuse, and in its place new systems were proposed periodically which likewise did not gain sufficient acceptance to take permanent hold. In 1936, when the calendar reform movement was at its height, American astronomer Robert G. Aitken published an article outlining a Martian calendar. In each quarter there are 3 months of 42 sols and a 4th month of 41 sols. The pattern of 7-day weeks repeats over a 2-year cycle, i.e., the calendar year always begins on a Sunday in odd-numbered years, thus affecting a perpetual calendar for Mars. Whereas previous proposals for a Martian calendar had not included an epoch, American astronomer I.M. Leavitt developed a more complete system in 1954. In fact, Ralph Menzer, an acquaintance of Leavitt's who was a watchmaker for the Hamilton Watch Company, built several clocks designed by Leavitt to keep time on both Earth and Mars. They could also be set to display the date on both planets according to Leavitt's calendar and epoch. Charles F. Kappan included references to Mars dates in a 1966 Jet Propulsion Laboratory technical report associated with the Mariner 4 flyby of Mars. This system stretches the Gregorian calendar to fit the longer Martian year, much as Lowell had done in 1895, the difference being that the 20th of March, the 21st of June, the 22nd of September, and the 21st of December marks the northward equinox, northern solstice, southward equinox, southern solstice, respectively. Similarly, Conway B. Leo Val. also expressed time in terms of Mars dates in a 1973 paper describing results from the Mariner 9 Mars orbiter. British astronomer Sir Patrick Moore described a Martian calendar of his own design in 1977. His idea was to divide up a Martian year into 18 months. Months 6, 12 and 18 have 38 sols, while the rest of the months contain 37 sols. American aerospace engineer and political scientist Thomas Gangale first published regarding the Darien calendar in 1986, with additional details published in 1998 and 2006. It has 24 months to accommodate the longer Martian year while keeping the notion of a month that is reasonably similar to the length of an Earth month. On Mars, a month would have no relation to the orbital period of any moon of Mars, since Phobos and Deimos orbit in about 7 hours and 30 hours respectively. However, Earth and Moon would generally be visible to the naked eye when they were above the horizon at night, and the time it takes for the Moon to move from maximum separation in one direction to the other and back as seen from Mars is close to a lunar month. Czech astronomer Josef Šorin offered a Martian calendar design in 1997, in which a common year has 672 Martian days distributed into 24 months of 28 days. In skip years, an entire week at the end of the 12th month is omitted.